Welcome to this puzzle session. Here is the puzzle that we're looking at. So it says that in a group or brigade of 7 people, the sum of the ages of all the members is some number, 332, let's say. Then we want to prove that among these 7 people, one can find 3 different people such that the sum of their ages, the sum of the ages of these 3 people is at least as much as 142. So if you know the sum of ages of 7 people, then there are some 3 people amongst those 7 whose sum of ages you can lower bound, and these are the precise numbers in the problem that appear. All right. So of course, as it goes for any puzzle session, you should pause the video and try to solve this yourself. All right. So let me introduce some notations. So I will write capital X to mean this set, the set of first 7 integers. And A1 up to A7 will be used to denote the ages of all the 7 people. So just label the people by numbers 1 to 7, and the age of the ith person is A sub I. All right. And I will use this symbol, which will be read as X choose 3, as the set of all those subsets of X which have size 3. So note that this is not a number. This is just this is a collection of subsets of X, not just some arbitrary collection, but only of those subsets of X which have size 3. So clearly the size of X choose 3 is a number which is mod X choose 3, which is 7 choose 3. Mod X is the cardinality of X. So the size of X choose 3 is a number, but X choose 3 is not a number. Alright, and also for any element of X choose 3, meaning for any 3 element subset of X, we will write A sub S to mean this number. So let me give an example to illustrate what I'm trying to say. So if S is, for instance, 3, 4, 7, which is a legitimate 3 element subset of X, then A sub 3, 4, 7 will just mean, this is a notation for A3 plus A4 plus A7. So that's all. So that's what, in general, this means. Okay, so these are just some notations. And now let me introduce a very simple fact, which I will call the averaging principle. This is like the pigeonhole principle, which is very simple to state and prove, but it can be applied in powerful ways. So suppose we have some real numbers t1 up to tn, and their average you have a lower bound on the average. So alpha is some other real number, and you know that the average of these n numbers is at least alpha. Then the claim is, or the averaging principle says, that there must be some I such that ti is at least alpha. So meaning at least one number among these ti's, or among these folks, must be at least alpha. And why is that? The proof is very simple. So the proof is this. If ti is less than alpha for all I, then clearly the summation is less than n times alpha, which implies the average is less than alpha, which is a contradiction to the hypothesis. So that's it, that's the proof. So it's a very simple fact. And this is what we'll use. So now for the solution of the problem. So here is the main observation. If we sum all elements, the summation is running over all elements of X choose 3, AS. So AS, recall, is the sum of all the ages of the people corresponding to the set S. Alright, so this number is equal to, I want to say this is equal to 6 choose 2 times summation I equals 1 to 7 AI. So this is what I want to say, and one can prove this completely formally, but let me argue somewhat colloquially. So here is how you can argue this. Just try to see how many times a given AI appears here. So for instance, suppose we want to know how many times A1 appear in this side. So basically I'm asking the question, how many subsets of X are there of size 3 in which 1 lies? So 1, 2, 3, 4, 5, 6, 7 are the numbers. You want to find how many subsets of size 3 of these 7 numbers are there in which this guy lies. So this we want to put in the 3 element set, and out of the remaining 6 elements we just have to choose 2 of them, and there are 6 choose 2 ways of doing it. So you can see that A1 appears in the summation 6 choose 2 times, A2 also appears 6 choose 2 times, and same goes for each AI. So this is equal to 6 choose 2 times the sum of all the AIs. But you can argue this more formally and you can convince yourself, but this is a simple fact. Alright, so what does that give us? The average. Now so how many terms are there? How many of ASs are there? Precisely the cardinality of this, which is 7 choose 3. So I will divide both sides by 7 choose 3. So 1 upon 7 choose 3 of this sum. So left side becomes an average, is equal to 6 choose 2 upon 7 choose 3 of this sum. And I know the value of the sum. This is given to be, I don't know, 332. Yeah, this is 332. So let me just calculate. So 6 choose 2 is 6 into 5 by 2. And 7 choose 3 would give me 3 into 2 into 1 divided by, let me put a 1 here also because that looks better. And divided by 7 into 6 into 5. So I'm just doing some basic high school level algebra. So we have that, and this is equal to, so this cancels off, and this cancels off, this cancels off. So we have 3 by 7 into 332, which is 996 upon 7. And this, if you compute, this is 7 ones are 7, and then 2, 29, 7 4s are 28, and then 2, and then point something something. Alright, so the conclusion is that this average, 1 upon 7 choose 3, summation s in x choose 3, as is at least 142. This is what we conclude. In fact, we know it is strictly greater than that, but doesn't matter. So this implies that there is some s such that as is at least 142 for some s. That's what the averaging principle says. Right? Let me put that in a different color. So this is the conclusion. Let me use maybe this color. Okay, so that's exactly what we wanted to do. What is this? This is the sum of the ages of the people in S. So some 3 people have the property that if you sum up all the ages, sum up the ages of those people, then you get at least 142. So that's what we wanted to prove, and this is it. So that's all. Alright, so thank you for listening, and I'll see you next time.